So that's Gaussian elimination method and Gauss-Jordan elimination method. I say so. Of particular interest, particularly in the Gauss-Jordan elimination method, we say it's used in finding the inverse of a matrix. So you can try that one. And then we did some assignments. So what do we do? So, let me hope my thing will work. So I can try to share here some code for Gaussian elimination method, and then you can modify. I think it's in Python, but you can have the same code in. You can transform the same code in any language you use. So I'll try to share the whole screen. So I'm waiting for my screen to share. So as the screen is sharing, if anybody has a question, you feel free to ask. Questions? Kama hizi siku hizi zimekuwa rahisi, mnaelewa? I will try to. I think I will try to share the whole screen so that I can now move what is happening. This thing. So if you see my screen, confirm that you can see my screen. Yeah. No, this. And so, do you see what I've shared? I don't know how I can magnify. That's now the good. That's a good thing. Let me see if I use Control Plus. Yeah, is that better? So I think you might be familiar with this. So I'm using Jupyter Notebook, so some of you might be familiar. So it's just something to run some of these things on the fly. So whatever I have here is just a code for Gaussian elimination method, which you can modify, and then you can add many things. So basically, I know you guys nowadays you use this your other friend. What is it? How is it called? To do things. So I wrote this code in MATLAB, and then I asked your friend to convert it to a Python language. So basically, that's what you can do. So in MATLAB, I'm more comfortable. I can write any code on the fly, just any. For some of these other languages, then I need some Google a bit. So what I do, I write the codes I want in MATLAB, and then I convert them to the language I want. Some of the things that I have to Google. So I wrote it, what I call it, so I wrote it in form of a function. So basically, if you want a script, you can just remove this, and then you have a script, and then you define, you call A and B. But so what I did, I just wrote as a function so that it can take in any A, any matrix A and matrix B. So these are the constants. So whenever it finds A and B, then it combines them into another matrix. So this is now what I'm calling the augmented matrix. Okay, yeah, I have the comment here. So I'm combining, you know that what that means. And so this augmented matrix, I am counting the number of rows. I think the number of, no, I'm just not counting, I'm pre-assigning. I'm just creating a zero vector. So I pre-assign the zero vector to the solutions. And this is the length of the variable. So n will be the length of what? The length of the variables. Let's see, shape 0. Yeah. And so we now create an upper triangular matrix. Once we form this augmented matrix, we want to reduce this augmented matrix into an upper triangular matrix. And so, why is this thing hanging? So what happens? I go through the variable I. So basically, the variable I is the indices, not the indices. So the variable I moves through the whole, is it what? Yeah, it goes through all the rows, and then you go through all the columns. And so for each I, what happens first is you identify the pivot element. And so once you identify the pivot element for each I, then you start with J onward. So if you recall what we did, once we identify the row, which is our pivot row, and then you reduce all the row below it. Mostly when you write messages, then I have to keep checking where the messages are coming from. Yeah, somebody raised the hand. If you have something, just speak, because mostly I can't see the messages. I have to go and check. Somebody had the hand up. Go on. Was it a mistake? No. So this thing is, so there are no questions. So what happens here, you identify the pivot element or the row pivot row, and then you reduce all the row below it. That's why now for the J is moving from I plus 1. So once we identify, if you are in the first row, then you reduce the second row onwards. It varies in these ranges. And what happens, I think there is something I don't know if we looked at, but maybe we will not look at the code. What happens if somebody gives you a matrix and you find that the first row has 0 as the pivot element? Then you cannot divide by 0. And then does not satisfy the condition for original form. So if you find that the first row or the row you are looking at has the 0 pivot, then you have to swap the row so such that the 0 pivot goes below. And so that's why I'm checking that what happens if if that element is 0. If it's 0, that's what I'm checking here. I have this a comment. I'm checking if that element is 0. And then I find indices where all the other J's are not zeros, all the subsequent J's, so all the J's below it. And once I identify where that is non-zero, then I swap, I interchange. I just take the first one. Once you get the first non-zero element, then you swap with the 0, 1. So that now the 0 will go below. So this is just to eliminate the 0 pivot. Whatever is happening on this part. Check if it's 0, then find the index of any element Cii along the same column, which is non-zero. And after, you swap that element with the first element, which is 0. So it will bring all the rows downwards. So if you don't check this part, this code will still work. However, if you will have any matrix with the 0 pivot element, then it will fail because you will not divide by 0. So that's what will happen. And so we define the multipliers as the same way we defined our multipliers. You find the multipliers. And once you find the multipliers, you now reduce all the subsequent rows by summing up the same row plus multiplier multiplied by the pivot row. And that's the only thing that you need. And until this part, this code until here, it gives you the triangular system, it gives you the row echelon form. Let me just put here, it gives you what? The row echelon form, because it's not necessarily the triangular form. And so once you have the row echelon form, then you can now, so from here, if you leave it until this point and then you display, it will give you the triangular matrix or the reduced matrix. Once you identify this reduced matrix, we now want to do the back substitution. Like, well, I think there's something I was telling the one who presented last week. That's so to do the last substitution, we know that we start with the last element. We divide, just take the solution part. This is the solution part, Cn1 and then n, then divided by Cn1, whatever, Cn. And then you divide them. Once you divide, you get this Cn1. And then the rest, you can now do the sum. Once you get the last one, you now apply the back substitution by just summing up, taking the answer multiplied by the variable, and then you keep summing up, improving. So that's why, so for the J onwards, I start with BB, whatever. This is just summation. I can just call this sum. Sum is equal to 0, and then you keep taking this sum multiplied by the solution you get. So this, until this point, it will give you all the solutions you do. And so here, I just make an output. I make an output. So once I get this matrix C, which is the row echelon form, and then I can make an output of now I can extract the triangular matrix. I extract now the B's after the reduced, and then I find the solution, and then I return this variable. If you want, I can still return here the C. Here, the C is being produced somewhere here. So I can also still return here the C, and then I compile this code. And so now we can apply this to any matrix. Since I've created another output, I can put here that output until this point. So once we have this output, then let me try to just print out one of these things. Also print out, this is what? Let me say, this is the row echelon form of a matrix. And whichever we need, and then I display here, C. And so if I say I run this code, what happens? You see, you get the augmented matrix Cn. This is now the matrix of the reduced triangular matrix. You can confirm. This is after reducing. This is now the right hand side, and this is the corresponding solution. Solutions are -1, 2, 0, and 1. And now this is now the full matrix, the full row echelon matrix. So this is just these two matrices combined gives you the last one. and this will be applied to, this can apply to any. Anybody who wants to try with any other matrix? Do you have matrix you want us to solve with this? I can just copy this code, and then I create another what? Insert another cell below. So, does anybody have a matrix you want us to try?
Yes, there was this one with the decimal places. It was 2.11.
2.11. But remember here, we are not applying the pivoting. So in this code, I didn't apply pivoting. I'll improve it to have the pivoting later on. Right?
Yeah.
So if there will be errors because of the pivoting, then we will not get a solution. We will get some, it might give us something different. But it's good to try. Next is
minus 4.21.
4.21. Then
0.921.
0.921.
Then 2.01.
0.01. And then also this, what I need to improve. Remember also, I've assumed here that all the matrices I submit will have solutions. So I still need to improve this code, that once you are here, if you check this and then you find it has 0, then you do something different. If it has no solution, then you stop and you don't output this part. It becomes, if it has many solutions, then you make the last guess. You guess this number. You just take -1, you give it a number like 1, and then you generate this other one. So that's what I need. I need to improve, and I'll have it in the next class. Let us proceed.
4.01.
4.01.
10.2.
10.2.
Minus 1.12.
1.12.
Then minus 3.09.
Next.
1.09. 0.987.
0.987.
0.832.
0.832.
Then 4.21.
4.21.
It was just the 3x3.
But why do we have here 4?
Sorry, the other parts are the solutions.
Okay, so this code I made is such that it works on it works on any of these. And so you separate the matrix and the solution, and then it will concatenate by itself. If you want to make the concatenated one, it's still okay. You make the concatenated one, and then you now supply what? You supply this part. I think I have to now remove this. I think I removed something extra, right? Yeah, and then the same also here, I need to remove this. Let's hope it works. And so once I have this, control enter. So it gives us here, the reduced matrix, gives us the vector of solutions. These are the answers we got.
Yes.
Yeah. So you see, that's how it works. Yeah.
Yes. Thank you.
So basically, this code. So I think, no, I don't know your names, but whoever presented last week, what I was telling you is that you make it such that the code can be applied to any. So when you get any matrix, you don't have to worry about the order of the matrix. So that's why you just apply any 8. These are the inputs, A and B, which are just any. This is a matrix. This is a vector, and then you combine them, you concatenate them, and then you look. This is just now finding the length of this along the shape 0, so the number of whatever, and then you keep doing. So this is just now. If you have this code, is not an issue, but so it's good to pre-allocate. You pre-allocate the spaces. Some of you who are good in programming, you know what that means. By just pre-assigning the spaces, and it makes the code faster. So it's easier to fill numbers in the pre-allocated spaces than having to create a new space for a different number when you get these matrices which are increasing. And so the key part, what I told you is, if you remove this part, then this code will fail in case you have a pivot row. It will fail. If I just comment on this part and then I introduce a pivot row, I can, no, we just want to, since we are trying, right? I can just make this number 0 here, right? But I don't know if it will have a solution. That's one thing I don't know, if it will have a solution. But so I'm just making this to 0. And then I rerun this. Yeah. Then, oh, it brings something different. Is it the one we have run, or maybe it was different? Good. Oh, this looks crazy. I don't understand what it means. No, but that's whatever happened. We don't care. But so the point is, this, even if you have a 0 as the pivot element, it will swap. But let me do that and maybe try to comment on this part and see what happens. Just I want to comment on this part, the if, and then I save the function and I run this new one. Okay, you see it did not do anything, right? Why? Because it kept this as very large numbers, very large. I think because of dividing by 0 somewhere. And so you get, in fact, you see it's complaining already, right? It could not proceed. And you see this comment I've told you. He's saying here, divide by 0 encountered a long scala, so it's dividing by 0. So that's why you're having these problems. So that's the purpose of this part. I said that I introduced this part here, which checks. But why today? Why do I have so many customers? Hello. Niko class, wacha nakupigia. Niko class, nitakupigia. So you now appreciate that part. So that was the purpose of what happened. And so when you make your code, you try to give it different scenarios, and then you keep improving. Like I told you that here I'm just checking I cannot divide by 0, but what I've not done on the solutions is what happens if I have a matrix that does not have solutions. Basically, you're having all the rows, there are zeros and something. You will have the same problem of dividing by 0 because you cannot divide here by 0. There are so many solutions. So if there are many solutions, then you need to make the first guess. You just guess because there are many. The last number can take anything. So just make the last guess and then introduce the others as you go. Is that okay? Or somebody wants to bring any other here? Was this one or was this one? Oh, maybe let me not. What was here originally? Was it 1 or -1? Whichever we have. Yeah, I think it was 1. But so if you want to take this, the only thing I want you to do is go and improve it and make sure that you are checking. So whenever you have many solutions, you give warning. But I don't say that you must use a function type. You can just have this as script. Whatever you just come in here as script until this point. And then you remove the return, you remove the function, and then you. So when you have this script, it means you have now to carry on these two parts and put them above so that you start with them. You define A, B, and then you continue doing this if you want to avoid the function. But if you have the function advantages, just create it, store it, and use come and bring the matrices. It's just like what you have this input. Instead of having that input A, input B, you just call them as a function. and they are just being called here. Call the name of the function you are using, and put the inputs A and B. Kuna mwenye ako na swali hapo? Ama if you want us to try something again, a different one, then you say. Do you want us to try another example, even 2 by 2 that you know?
I have a question.
Yeah.
I have a question. In the first class, remember you talked about round of errors and how this program sometimes they can bring wrong values because of the round of errors.
Yeah.
Could you kindly now explain a bit more what you meant by the round of errors?
You see, most of the examples we have done here, right? If you find the pivot, then you can express as a fraction. For example, if I take this as my pivot, and then I divide everything by 1, then you see you are just having whole numbers, right? Assuming, let me assume 3 was the pivot, and I have to divide everything by 3, right? You will have 2 divided by 3. Manually, if you are writing manually, you can write this as a fraction. But the softwares, these programs we use, laptop, calculators, whatever, they don't know fractions. They only know decimals. And they have their precision to which maximum the number of decimals they can accommodate. So if you have, for example, if something is working to 15 decimal places or 15 significant figures, then if you have 2 over 3, it will round off that value to 15 significant figures. So you are not using the exact 2 over 3. You are using an approximate 2 over 3. And because of the division, if this number is too small, for example, 0.001, let me see if I can get something here. Another one. Okay, I just want to, yeah. So for example, let me print here what? Even 4 divided by 7, right? What do you have? What is 4 over 7? So whatever this printed here is not 4 over 7. It's an approximation of 4 over 7. And so when you, let me just first ask this: did you do errors? Did you look at numerical? Did you do any numerical course?
No, this is our past numerical.
Then maybe they didn't set up your syllabus well. There's nowhere you looked at errors. So maybe. So if you divide by a smaller number here and you want 4 significant figures, for example, if I put here 0.7, then if you introduce errors and you want 4 significant figures, the smaller the denominator, the more error you accumulate and the more error you propagate. So when you look at errors, you look at error propagation in division, in multiplication, and in the addition and subtraction. And so that's why if you want the significant figures, the errors will be smaller if you divide by largest number. But if you let the numerator to be bigger, then you are increasing the errors when you round off. So basically that was the thing, that if you do manually, you can write in fractions. But if you are using the calculators, the computers, the phones and everything, they don't know fractions. They try to approximate values to their precision. And so because of that precision, if you have smaller pivots approximately close to 0, then you are accumulating very large errors, which will also accumulate in the solution. And if you do an example, you don't if I give you an example, you can see round of 4 significant figures, you can see the effect of that one. That the more you approximate, the more you propagate the error going forward. I don't know if that one gives you a hint of what it means.
Yes, it does.
Yeah, so to reduce the errors, you want the pivot to be bigger. Whatever you divide with to be bigger number, and then if you divide by bigger number, then you are decreasing everything. So errors are not so large. And so in the same, this code you can also be easily applied with partial pivoting. And so partial pivoting also is also the same thing. You can check it here. Instead of checking only where this is 0, you check along that row, you check the largest element, and then you swap. That becomes the pivot one. So that's what you can do. But remember, largest in magnitude. And so to make the code with the partial pivoting is easier because it's just the same thing as this. Instead of checking this to be 0, you are checking which of these CIIs or CI then J is bigger, and then you swap. You make it the pivot one. And remember, bigger in magnitude, not bigger in value. Any other question?
Yeah, I have a matrix. You should try.
That you want us to try?
Yeah, it's 2 by 2.
Let me just copy the same thing, and then we will edit the matrix.
So it's 2 by 2. That's 2, 1.
2 and
then
1. So we don't have this guy, right?
Yes.
And then next
1, 1.
1 and then 1. So I don't have this guy, and then I don't have this guy, right? And then here
5.
5
and then 2.
So what are the answers to this?
It doesn't have.
It does not have.
Yeah.
Then I told you this will fail, right? Well, the determinant is what? The determinant is 1. No, but it should have. This has a solution, unless if you go to maybe it should have a solution. Okay. Oh, okay. I see. So if we reduce it, can somebody reduce it manually? What do you get? You have 2, 1, 1, 1, and then you have what? You have 5, 2. And then I multiply this by the first one. So the first one remains as 2, 1, 5. The second one, I multiply the second one by 2, and then subtract from the first one. That will be 0. That will be minus 1. No, but it has a solution. Why do you say that? I don't understand what's happening. Why do you say it does not have a solution? I think there is. But are these rows independent or dependent? I don't understand.
Okay, when I solved with substitution, I was getting the value of x to be 3, and then y 0, and then now you get a situation where 6 equals to 5. So that's where I was saying.
No, I
Maybe
still don't have.
I'm having a solution.
I still don't think, because you are solving the system as 2x, right? Plus y is the same as 5, right?
Yes.
And then next is x plus y is the same as
2.
2. So if I just subtract them directly, then I'll have x is the same as what? X is the same as 3.
Yeah.
And if x is 3, y is the same as -1.
Okay. There's a solution.
Yeah?
Yeah, there's a solution.
There's a solution, but why is this one also misbehaving? And it's also getting that wrong thing. So let me first up. Let me update this and update this to see if I'm getting the correct values, and update this. And finally update this. But still this one does not make sense. And so it means in this code there is I think there is a problem somewhere in the code that I need to check. Let me just change these values and then see what happens. So this is bn. Did we change anything? Did we change anything somewhere? Let me see there. So the function takes this, checks the shape, gets these values, and then you are in the range. If this y is equal to 0, then you are having this indices swap. Then you have minus CII. Then you multiply this by values, then you do back substitution. And then for I in the range of this. No, I think there is a mistake somewhere that I cannot understand. No, I will check the code. So it's good that you have brought out this. So when you get these things which are failing, then you think more of what is happening. And so it means it fails on a 2 by 2. I will see what is happening, because I cannot figure out what is happening. And seems to be nothing. Let me do this. Let me also, I want to output so many things. So I want to output n, and then I output what? I output c. No, but yeah, c is being up. Yeah, I want to output c already. C, we are having an output. C is concatenate this, and then you keep on doing this. That's now, yeah, but so C will not concatenate this. But let me just output 10, and after I output here this, I need to update this. So this is what programming does. Some of these things, let me see where is n. Let me put n to be the first one. I have to print out n. N is 2, which is just which is okay. But why is it not working correctly? Why is it? Okay, so apparently this does not work on 2x2. Does it mean that way? Because if you put here any 2x2, then you don't get a solution. But what happens if I make them to be the same? Now this one does not have a, so this one is okay, it does not have a solution. But so once I put this -3 where you just add and then you have, this is 2, this should, but this works. So why does this work and the other one does not work? Anybody who can think through this? Did we mess up in the code somewhere? Oh, these are democratic. This is just okay. And then you are checking the index. No, for now, leave it that way. I will check what happens. Why does it fail? So we go to what we wanted to cover today. So we wanted to look at the last method, which is called the LU factorization. And LU factorization, just as the word says, it says that if you have any matrix A, so just say, so I'm writing here that any moving this up slightly, that any matrix A, not any matrix, so it is any square matrix A can be written as a product of upper and lower triangular matrices. That if you are given any two matrices, no, any square matrix, then you can write that matrix as a product of what? Lower and upper triangular matrix. That means we can write this A as what? As LU. That's what we mean. And remember, L and U are not unique. So you can decompose any square matrix as a product of triangular matrix, low and upper triangular matrix, and it's never unique. You can get different one depending on what you fix. So if you want to get the unique L and U, then you have to fix the diagonal elements of one of them, either L or U. And so that for L and U to be unique, then fix diagonal elements of either L or U. You fix diagonal element. And I think when you fix that one, I think if you fix them to be one, I think it's called something like Cholesky factorization. You can check what that means when you fix this. So we can apply this to any simple matrix, any simple 3 by 3 matrix. Can somebody give us any matrix? Matrix 2, 3, 2 minus 1, 4, and then 3, 2, 1. Oh, that's just a reverse of the other one. Maybe let me put, so I'm trying to avoid it to be just not have 0. But if it has also no problem. And so this, we say that this can be written as a product of what? Of L, L and U. So I'm just writing here any general L and U. And for now, I will fix diagonal elements of L to be 1. But you can also fix the diagonal elements of U to be 1, and then you get a different factorization. And so I can have this is 1, then L2 1, no, this is 0 1, L1 2, L1 3. These are 3 by 3. That's 0 1, L2 3, 0 0, and then 1. And then multiply by upper triangular matrix, that will be U1 1, 0 0, U2 1, U2 2, 0, U2 U3 1, U3 3, and then no, this is U3 2, U3 3. So this is what it means. And so you need to find this L1 2, 3, L2 1, U1 1, and so on. And if you look at, if you go, you do this and then you do them continuously, you will see that there is a way. If you start it, then you get it easily. You will not form so many questions. You will form these values, and then as you keep going, you keep generating different values and so on as you go. And so you just need to identify which one you start with, where, and how do you multiply, so that you could easily single out the one you want to start with, and maybe it becomes easier. So you did not tell me that I wrote these matrices wrongly, right? I'm supposed to reverse them. So this is supposed to be lower triangular matrix. This L. So this is a lower triangular. This is an upper triangular. So this is L2 1, L3 1, L3 2. Then these are 0, 0, 0. And then U1 1, U1 2, U1 3, U2 3. And then I have 0, 0, 0. Yeah. So it's supposed to be this way. And so if you multiply, so how do we get U1 1? So this is an example. How do we get U1 1? You multiply this side and equate to the values on the other side. And if you, depending on which values are fixed here, will tell you if you need to multiply along the rows or along the columns. You go systematically. You go rows onwards or you go column wise. That one you can generate solutions. So can we try to generate these values? So you know matrices. If you multiply matrices, then the first element will be the same as the first element on the other end. So for example, if I take the first row multiplied by the first column, you know that matrices multiply row by column, row by column. And so if you take that first row multiplied by the first column, what do you get? You find that U1 1 is the same as 1, right? Is that okay? Tell me if that's okay.
Yes.
Yeah. So once you get U1 1, and then you proceed. So I know somebody may go to this and this. But remember, if you go to this line, then you have two unknowns. So since you have these ones are known, then you can multiply, you multiply all the rows by the first column, and then go to the second column and that way. That way, but even if you go the other way, it's okay. It's only that you'll be having unknowns and then you have all of them, which takes time. But if you go systematically, like, if I multiply, for example, this second row by first column, what do we have? I'll have L21 plus L21 multiplied by U11, and then plus, the others are zeros. You get what? You get 2, these two here. So if I do this, multiply by this, then I get 2. So that's how that's the position. So what does it mean? This means that L21 is 2 divided by U11, which is 2. Is it okay? Then in the same way, I can multiply the third row and first column so that I have L31 multiplied by U11. The rest are zeros. That's why I'm leaving them. Will be the same as 3, meaning L31 is 3. So if you go that way, if you identify the direction in which you go, you generate these values sequentially as you get the next values. You will not accumulate n unknowns, because n unknown, you get it, you can get it from the previous value. But if somebody would have gone the other way around, that you have multiplied by this, then you will start by first accumulating the unknowns and then start evaluating them, where you can make some mistakes. So I've finished everything with the first column. Then I can now do the same with the second column. The second column, so let me say maybe this is just so that you can keep track. This was multiplied by column 1 of U matrix. Now I can go to column 2 of U matrix. What's column 2 of U matrix? I multiply everything again by column 2. In the first one, I'll have what? I'll have U12 multiplied by 1 is the same as 2. Make sense? And then I multiply now the second row by that column again, where we will have L21 multiplied by U12, and then plus U22 multiplied by 1 is the same as so is this element here is the same as -1. But so you remember here, you have L21, you have U11, so you don't struggle because you have these values. And then I can say that U22 is the same as -1 minus this product. L21 is 2 multiplied by U12 is 2, which will give us 5. I think because it's no, it's not 5. So it's -5. So you see that in each computation you do, you are not accumulating any unknown. Once an unknown comes in, you get it, and then you move to the next one. As opposed to if you do the other way around, then you find that you accumulate unknowns, and then you have to see where to get their values from. But in the end, you will get the same solution. Once you fix diagonal rows of one of the matrices, either upper or lower triangular, then this factorization is unique. But however, if you don't fix this, then the factorization is not unique. Any question? So I can go to, I think, the last row with the second one. So I'll have L31 multiplied by U12 plus L32 multiplied by U22 is the same as, because this other one is 0, is the same as 2. So this gives us 2. And then what do you have? We have L31. What is L31? Is 3 multiplied by U12 is 2, and then plus L32 is, we don't know L32, right? So I'll have here minus 5, L32 is the same as 2. So this is positive, that's minus 1. That means L32 is the same as 1 over 5. No, is it 1 over 5? No, that is 6. 6, 2 minus, that's minus 4. So it will be 4 over 5. Just to check that it is, we got the correct values. But so basically, this is how you solve them. So you can do the same way, and then you also solve for the last value. And so you can get all the U's and all the L's, and then you can now get, you can write the matrix A as a product of this factorization. But so the question is, how do we write? So compute this and then you get all those values. We want to see the application. So to solve the system, Ax is equal to B by LU factorization, we consider, so where there is A, we know that A can be written as what, LU, and then multiplied by X will be the same as B. And so I can write, this means, this implies what? I'm just having LU X the same as B. So this is a vector. A matrix multiplied by a vector, you get a vector. So I can say let this be Y. So that now you have Ly is the same as B. And so if you have a triangular matrices, solving them with unknowns is easier. And so if you have L, solve for Y by forward substitution. It's opposite of, when you have an upper triangle like in Rachel form, then you solve by back substitution. It means you start getting values from below coming upwards. But if you have a lower triangular matrix, then you start solving from upwards coming downwards. That's why I'm calling backward substitution. Once you have this, then solve for X in Ux is the same as Y, because you will have gotten Y here, and then you bring the Y's here, then you solve for by back substitution. So the only task you have is just expressing L and U, finding L and U, and once you have them, it's just you solve either by back substitution or by forward substitution, and you will be done. And that's the only thing you need. So maybe let me do this and then we can do one example. Let me first write the inverses. How do we finding the inverses? How do we use LU factorization to find the inverse? We know that L is the same as LU, right? That's what we know. I can multiply by A inverse either side. I can multiply this by A inverse, then I multiply this by A inverse. What does it mean? You know that a matrix multiplied by the inverse gives you what? Gives you identity, the same as A inverse LU. And so maybe I need to leave some space here. So I can also multiply here by U inverse and multiply here by U inverse. And so if I multiply this by U inverse, what do I get? I'll get that U inverse is the same as A inverse multiplied by L, because this is just the identity. And then I can multiply by L inverse, I can multiply by L inverse. Well, this also gives idea. What does it mean? It means that A inverse the same as what? U inverse, L inverse. That once you have found U and L, then you can find their inverses, and then you find the inverse of A just by now swapping, multiply U inverse by L inverse. And if you want to have the determinant, then determinant of A the same as what? Determinant of U multiplied by determinant of what? L. And if you have a triangular matrix, finding the determinant is very easy because you just multiply elements along the main diagonal. So it means the determinant of A will be the same as what? U11, U22, multiply by L11, L22, L23, etc. Just multiply all elements along the main diagonal of all diagonal elements. So that's about an LU factorization. And then if you want, we can do an example and we call it a day. Or if you want to go do an example at home, it's still okay. Because the only thing is just express the matrix in terms of L and U. And then you can now solve it by forward substitution, then followed by back substitution. Kuna mwenye ako na swali? Anybody with that question? So should we call it a day? But example is just you to do it. If you will be faster, then we can do an example.
Yeah, I have a question. The discussion, the LU factorization, it looks a bit similar like the eigenvectors and eigenvalues. Do they have a similarity?
All these things are related. Eigenvalues, determinant, Reuter form, whatever. If you express a matrix in the Gaussian elimination method, it relates to the determinant, which in turn relates to the eigenvalue. So all of them are connected. But basically, these are not. Maybe in the sense in which you look at them, not so much. But yeah, they have some relationship. Because if you have a triangular matrix, the determinants are simply the elements along the main diagonal. Those are the determinants. No, not the determinants. Those are the eigenvalues. So the difference here is that for the eigenvalues, eigenvectors, you have a vector x, but here you have both of these are matrices. But all of them are connected to this. So can somebody give us an example? The matrix. So remember, I'm just starting with L. So it is L. Which one do you want us to fix? No, give us matrix A. Matrix A is just pick from negative 3. Uh-huh. Uh-huh. No, to illustrate, let us only do 3 by 3. If you have a 3 by 3, it's okay. It's enough to illustrate. Yeah. 6 where? 6. Uh-huh. And what are the B's? Because we are writing X is equal to B. So what are your B's? Mm-hmm. Are you guessing this, or maybe you got them from someone? If they are, if you get the crazy ones, we might get crazy solutions. But basically, so we can fix any of the rows. We can fix. In this example, I fixed what? The lower triangular. Yeah. Okay. So first matrix. Okay. Yeah. Read the values. Mm-hmm. And the B's. Uh-huh. So the first task is decompose the matrix A into lower and upper triangular matrix. Most cases in the exam, when this happens, I will tell you the values you fix in the data so that we have unique solutions. If we leave it open, it means each one of you will have a different LU and all of them will be okay, but the solutions will be the same. So for now, we can try to fix for the U because the other one we fix for the L. So I can, this will be L11, 0, 0, L21, L22, 0, L31, L32, L33. Remember that the order of L should be the same as the order of the matrix. Then I can fix this as 1, U11, U12, and then 0, 1, U13, 0, 0, 1. And so we start generating these values. If you fix, remember, if we fixed L, we were taking all the rows of this multiplied by the rows of the columns of U. But now if we fix U, you take one row of this and multiply by all the columns. I think, yeah, I think that what works. We will see what happens. And remember, I'm just fixing this to be ones, but you can fix this to be any values. You can even give them different values, 1, 2, 3, or different one. So we want to start. Can you start with the first row? What is L11?
Two.
L11 is equal to 2, correct. What is U11? What is U11? Oh, let me change some, but I don't know. I can change one thing and then it messes up everything again. I know this is 2. I've seen a fraction is coming. Let me try to avoid just the first fraction and fix this element to 2. This is taking time to respond. But why? So if I can put this to 2. It's just guesswork. Let me put them all of them to 2 since they are 2. But just guesswork. We can get that maybe we go into a more difficult thing. But so if I fix that one to 2, what is L11? L11 is 1. Yeah, correct. Because you are having this multiplied by this will be the same as 2. And what is U11? Remember the other time I was going all rows by column. Now I'm going one row by all the columns. What's U11? People are sleeping. I'm just taking this, multiply by this. If you are not sure, just multiply them, put aside, and then start equating. For example, you can just say you are forming the whole of this matrix. Then you have a bigger matrix here, which will be the whole of this multiplied by this is 2, L11. This multiplied by that will be U11 multiplied by L11. Oh. This multiplied by that will be L11 multiplied by U12, etc. And then you can do the same to the other rows. Will be the same as 1. No, this is 2, 1, 2. And then you start equating these values. So if going step by step confuses you, just multiply these two, form the big matrix. And you know what we said, that two matrices are said to be equal if their corresponding elements are equal. So once you form this big matrix here, then start equating different values. And then you get the solutions. So if you are okay with that one, please proceed. It's okay. And if you are still maybe practicing to get a result with this, then it's better you can do that one. And then what is U12? Right?
2.
2.
And then we proceed. What is L21? Did I do something wrong? So because I just took this, multiply by this, and then I equate to 1. So I was avoiding fractions, but now fractions are still coming. And then I go to this, multiply by this. I'll have what? L21 multiplied by U11. Then plus 2, L22 is the same as what? Is the same as minus 3. So L21 multiplied by U11 is a half, right? So you get that L22 is the same as what? Minus 3 and then minus a half. That's the same as what? Minus 7 over 2. So it will be minus 7 over 4. No, that will be L22. If I make a mistake, you check. And then last one, we multiply this by that. You will have L21 multiplied by U13. Yeah, that's U. Oh, oh. I wrote these values, but don't worry. We just find them. I wrote them wrong positions. But it's multiplied by U12. So this by that, and then L22 multiplied by U13. L22 multiplied by U13 is the same as the last one is 0. It gives us 3. And so you check what are these values. So U12, what is U12? U12 is 2 multiplied by L21. L21 is a half. So that gives us 1 plus L22. What is L22? U13. Oh, unless we made a mistake somewhere. L22 is supposed to be somewhere. Okay, yeah. L22 is minus 7 over 4 multiplied by U13 is the same as 3. And so if that one goes there, minus, so it is 2. So it is U13 is the same as 2. That is 8 over minus 8 over 7. Can you confirm if that's okay?
Yes.
Now can you find the remaining values and tell me? Find all those remaining values. And if you find, and whoever finds them, you tell me so that I fill this matrix. Let me see the values we found. We found L11 to be 1, and then 0, 0. And then we found U11 to be 1. First of all, this is 200. And then we found U11 to be 1. That is 1. We found, so it is 1, 2. And then 0. And then we found U12. What's our U12? What did we find as U12? Is 2. So that is 2. We found U13 as minus 8 over 7. And then this is 2. Oh, so we are almost done. So we found L21 as a half. And then we found did we get L22 somewhere? Yeah, L22 is minus 7 over 8. And then this is 0. Tell me the last row, L31, L32, and L33. If you have them, tell me. Mm-hmm. Mm-hmm. And the last L3, L33. What's that value? So you can go and finish that. But if you have these two values, I don't know. That's why somebody can miss this, because you have already this. You are just multiplying. You are just mapping this row multiplied by this and equate to -1, and you already have all these values. So if these two are correct, I don't understand why the last one is. It take time. Yeah, they are here. Which one? Yeah, you can name U23, but I named them differently. So if you name it U23, will be the same as your what I call here U13. So what is your value? What is your solution?
I find it to be -43/14. Maybe someone can confirm.
This
-43/14.
this part. So you people can check you can check later on if that is correct. I don't know if, because I've not done it, so you can cross check to see if those values are correct. Now remember, now we were solving this is the same as the right hand side was what? 8 minus 4 and 1. So this is 8 minus 4 and 1. So what we said, so remember, so we are solving this is x, y, and z, right? The same as these values. So we start by assigning this to an unknown, call it y. And then now we solve your L, which is 1, 0, 0, a half, minus 7 over 8, and then 0, 2, minus 1, minus 3 over 14, and then into y1, y2, y3 gives us 8, negative 4, and then 1. So just check, I'm still saying, just check to make sure that nobody messed. If you messed up this, then everything will mess up. So by forward substitution, it means you start from above. Here it means what? Your y1 is 8. That's what it means. Then you go to the next one. y1 over 2 minus 7 over 8, y2, the same as minus 4. So that is 4 already. Yeah. So this is 4. That's negative, negative goes. So it means y2 is the same as what? 16 over, huh? Not, yeah. y2 is the same as 16 over 7. Just check that is the correct answers. And then having seen this, so we proceed now to y1, 8, and then minus y2, so minus 16 over 7, and then plus minus 43 over 14, y3 is the same as what? Is equivalent to 1. So this is 16 over, yeah, oh, multiplying this will be, that is minus 14 over 43 into 1 plus 16 over 7, and then minus 16. So simplify that. Hmm? You get? So this negative 14 over 43 multiplied by 170. Okay, over 43. So once we get these values, and then we now solve the back substitution. So the back substitution now is, what is the back substitution? So the back substitution is, just tell me 2, 1, 2, that's 0, 2, and what? 0, 0, 2. This value was negative 8 over 7. So this is negative 8 over 7. And then into y1 is 8. So that is 8. That's 16 over 7. And this is 178 over 43. Then you can now get those values. Oh, let's see if these values are the same as what we can get with these other methods. The one who gave us, do you know the solutions? Is it something close to what we are getting, what we are going to get there? So it means somebody messed up on the. Let me check. I want the 3. Do I have a 3 by 3 somewhere? I want to copy the 3 by 3 somewhere. These are 3 by 3. I want to copy this. So can you read to me these values? Mm-hmm. Yeah. Uh-huh. And this. Mm. Mm-hmm. Mm. 4, 2, -1. Is this the matrix you gave us, right? This was 8. This was -4. And this was 1. I think we put something an n in the output. Let me check in the function. Yeah, we put an n in the output. Since we put an n in the output, is this your solution? Something like 3. This 1 and this -1 and a third. That means what? -4/3. This 4 and 2/3. That means 14/3, right? Are those the solutions? What are your solutions? -1, 4, and 3. So where are we getting the decimals from? Yeah, so this gives us 3, right? And if this is 3, I multiply this by 3, I get 6. 6 minus this minus 14. Unless I wrote something wrong here. Is this the matrix you gave us? Oh, can you confirm your solution? I doubt if this one can give us the wrong one. I doubt. But so with this, it's not giving us the solution. It means somebody has to cross-check all these things and then just go and do practice. Make sure, because once you get these things wrongly, I don't know, where did we stop? We had gotten up to which value? Up to U13. So something having U13. And then we can go to this last one. So here I'll have something like L312 is the same as 4, meaning L31 is the same as 2. And then this with this, it means 2 multiplied by U11. What is U11? Multiplied by 1. And then plus 2, L32 is the same as 2. Meaning L32 is the same as 0, right? Is it so?
Yes.
Yeah. So this is the first mistake. So just go back and check that this value is 0. And if this is 0, what is the next one? So the next one we have L311, L31 multiplied by U12. So it is L31 multiplied by U12, and then plus L32 multiplied by U13. L32 multiplied by U13, and then plus the last one is L33 multiplied by 2. So plus 2 L33 is the same as minus 1. So I told you that if you are not sure, multiply the left-hand side alone, get the bigger matrix, then start equating the corresponding values. What is L31? Just quickly. L31 is, we got as 2. And what is U12? It's also 2. So that's 4. No, but so if you, so this is 0, because one of them is 0. And then plus 2 L33 is the same as minus 1. That means L33 is the same as what? Minus 5/2. I hope we are not wrong. So I'm getting that this is minus 5/2. And then you can now check. So this is minus 5/2. So y2 is y2/7. And then you can now get y3. You check this other value, so you can go back and check. Just go back, go through this. I highly doubt if whoever is saying that, no, but we can stop here. Just let me write it down. I highly doubt if this, maybe if this gave us a wrong solution. That's what I highly doubt. But let me just write it down so that I can confirm is 2, 1, 2, 1, minus 3, 3. Also, just also go sit down and also check them. X, Y, Z is the same as 8 minus 4 and then 1. So go and check them to see if there's somewhere you left out in the solution or there's a mistake somewhere. But that's done. So LU factorization, just make sure you get the correct L and the correct U. That's why only where the task is. And once you get those ones, then you can get the standard of a matrix easily. And these are the parts. So we call it a day, unless you people have questions. So see you next week.